Good morning, everybody, or good afternoon, according to the place where you are. I hope you can listen to me. We are honored as Oceanic Engineering chapter of Italy and the technical committee of remote sensing of the Oceanic Engineering, but I will give the words to Ferdinando Nunziata, to have today our first conference on remote sensing, oceanic remote sensing, by Chris Roof. He's a very well-known scientist all over the world. And I don't want to give him all details, but it's very famous in several applications, especially in the use of remote sensing for tropical cyclone meteorology. And he was a recipient of very important awards. He's a fellow at IEEE. I don't want to give you much more details than give the word to Ferdinando, the technical chair of the Oceanic Engineering Remote Sensing Committee, and then to have my invite is to enjoy Chris Roof's seminar on a very challenging and important topic on plastic monitoring. Ferdinando.
Yeah, good afternoon to everyone, or good morning. This is the first seminar of the list of webinars. And even from my side, I'm very happy to host Chris Roof for this very important seminar. I think even the topic is very interesting. Nowadays, we are facing a lot of problems related to plastic in the ocean. So it's very important to see what are the benefit of remote sensing to this kind of application. And I think that this seminar is very important, both from operational viewpoint, but even from a theoretical viewpoint, because it's very largely under studied the role of microwave remote sensing for the observation of microplastics. So I'm very happy to see which is the benefit and which are the drawbacks on which are the opportunities in general that comes from microwave to the observation of microplastics. So let's give the word to Professor Chris Roof, and thank you again for accepting this invitation.
Yes, thank you very much for inviting me. And let me pull up my slides and begin my talk. Okay. I'm going to be presenting a particular application of a new NASA microwave remote sensing mission. The mission is called Cygnus, and the new application is detecting and imaging ocean microplastic concentrations and imaging how they change over time, their dynamics. But I wanted to start with a little background about this mission and its original scientific objectives, because it was not originally intended to do these types of measurements. But we've fortuitously found that we have this sensitivity to the presence of ocean microplastics that we've been able to leverage for this new application. So the original mission, the original Cygnus mission, was intended to measure ocean wind speed, and in particular measure ocean wind speed in tropical cyclones and typhoons and hurricanes. Because of this particular application, there were several features of the mission design that were considered high priority. One of them was having many satellites. So there's 8 satellites in this constellation, and we needed many satellites in order to be able to have a high revisit time everywhere in the tropics, so that we could see rapid changes in the development of the storms. And the other was to use a very low microwave frequency, so that we were able to penetrate through the heavy precipitation that is common in large storms. And both of those two features, the low revisit time and the low frequency, it turns out are very fortuitous for supporting the microplastic measurements. So we were kind of lucky that way. The mission is the satellites are in a very low inclination orbit, 35 degrees away from the equator, And because of that, we only make measurements between about 38 degrees north latitude and 38 south latitude. So that's a restriction on our ability to measure anything. The satellites were launched into orbit on one rocket, all 8 of them on a single rocket in December 2016. All 8 of the satellites are still working fine. And it's been up now for a little over 5 years. And in that time, you know, we've executed the tropical cyclone scientific objectives, but we've also expanded the science focus to many other areas. Over the ocean, the microplastic area that I'll talk about today. We've also generated new data products related to sensible and latent heat fluxes from the ocean into the atmosphere, which are useful for other meteorological applications over the ocean. And then over land, we've found a strong sensitivity to soil moisture and also an ability to image inland water bodies. And the inland water body sensitivity in particular is something that also has direct applications for not ocean microplastics, but inland microplastics. And I'll talk a little bit about that towards the end of the talk today. So the basic idea of this type of radar, it's a bistatic radar, not a traditional satellite radar. And it's bistatic in the sense that the transmitter and receiver are separated. So the transmitters that we use are transmitters of opportunity. We use the GPS navigation satellite constellation as the transmitter half of the radar. And then our satellites, the Cygnus satellites, have modified commercial GPS receivers. And they're modified in a way that allows us to measure the GPS signal after it reflects off of the Earth's surface. And when it measures the reflected signal, it can calculate exactly how the surface distorts the signal. And that's how we get information about the surface properties. If the ocean were perfectly smooth, it would act like a mirror, and you would get a perfect reflected version of the GPS transmitted signal. And this picture gives you an example of what perfect specular reflection looks like at optical wavelengths, where you can see the direct signal is the moon above the lake, and then the reflected signal is the moon reflected off the water. And if the water is very smooth, then you get a sharp picture of the reflected moon. But if there's wind blowing over the water, then the reflected signal from the moon is scattered in a diffuse way. And if you can measure that diffuse scattering, you can derive properties of the ocean surface, its roughness properties. And that's how we measure the wind. And it's also how we measure the microplastics, is by the disturbance of the surface. So this is an example at optical wavelengths. And then this is an example of the types of signals that we measure with Cygnus. So this is a GPS signal scattered off of the ocean surface when it's windy. And this bright red part at the top is the specular point, where the signal would be concentrated if there was no wind. But because there's wind over the ocean at this point, the signal is spread out over a broad diffuse scattering area it's called the glistening zone in optics. And we're able to resolve this. These two axes are the Doppler shift of the signal and the propagation time of the signal. So by range gating and by Doppler filtering, we can make an image of the scattering cross section of the surface as a function of position away from the specular point. And here's an example of 3 different similar types of measurements at different wind speeds. And you can see as the wind gets stronger, the surface gets rougher, and the scattering becomes more diffuse and more dislocated from the specular point, where it would be concentrated if there was no wind. So just a few quick pictures of the hardware. This is a picture of one of the 8 satellites when it was being tested in the laboratory. And here's a picture of 8 of them, or rather 4 of them, going into a thermal vacuum chamber to test their operation at cold temperatures with no atmosphere. And this gives you a good idea of the size of them. They're about 25 kilograms each, and I think about 50 centimeters across. And here's one of the science antennas right here down on the bottom. And then this is one of the satellites having its solar panels tested, the deployment mechanisms as they open up after launch to make power. This is a deployment module that all the 8 satellites were mounted on at launch. And then here are the 8 satellites mounted on the deployment module. And this is on a vibration table to make sure that everything is mechanically strong before launch. And then here is all 8 of the satellites being installed on the top of the rocket. So the rocket goes back behind the page here It's a small rocket, actually. It's about 60 feet long, 20 meters long. And then the 8 satellites go at the very top. And then this is the fairing that covers the top of it at launch. This is an animation of what the deployment looks like after launch. Whoops. So after after launch, the satellites get up into a low Earth orbit as a group, and then they get deployed by the deployment mechanism in pairs, and that sends them out at slightly different angles relative to the velocity of the orbit propagator, and that allows them to slightly shift to different altitudes and then spread apart to different distances. And now they're spread out pretty evenly around the orbits, the circular orbit, and that's how we get our sampling. This animation shows you what the sampling looks like as they're orbiting along. So all 8 of the satellites are in a common orbit plane spread out, and then each one of them has 4 GPS receivers, and they're looking down at the ground, making measurements of the scattered signal. These blue ellipses, those are the locations of the specular points reflecting the GPS signal. And as soon as one of those specular points enters the antenna pattern, that's this red circle here, when it enters the antenna pattern, we begin taking data, and we make measurements of that scattering, the GPS scattering signal, as long as the signal is within the antenna pattern. And as a result of that, the measurements that are made are these long blue lines, which are measurements of the scattering cross-section along the line, or those are transmitted or transferred into measurements of the wind speed along the line, or for the microplastic problem, they'll be translated into measurements of the ocean microplastic concentration from the scattering cross sections. And yeah, and here pan back is show you how the global sampling happens over time. We have 8 of the satellites spread out around the orbit plane. You can see that they only go up to about 38 degrees north latitude, 38 degrees south latitude, and these are the ranges over which we make our measurements. Okay, this is an example of the data product, the wind data product. This is from just a few days ago. This is the most recent data that's on the public data server. So these are winds measured on January 16th by all 8 of the satellites composited together, and you can see how the how the orbits are moving, or as the satellite orbits and the Earth rotates under the orbit plane, you get this map. And you can see there's several different major storms at different places in the world that this picks up. There's one storm here in the West Pacific, another storm here in the North, several in the North Atlantic, and then another one in the South Pacific down here that we're picking up from the wind speeds. So this is the basic data product that is used for the ocean wind measurements and for the tropical cyclone applications. And I wanted to give you just a couple of quick examples of some of the scientific applications that we're using this data for, other than the microplastics, and then I'll spend the sort of second half of the talk specifically talking about the microplastic application. So this is an example of some of these same types of measurements that are made as we flew over a particular hurricane, Hurricane Dorian in 2019. These are subsequent sequential overpasses of the storm. We go over, excuse me, at most latitudes, we go over a storm 2 to 3 times a day. At this latitude, it's twice a day. And you can see an overpass here at 10 UTC, and then 18 UTC, and then the next one on the following day, August 30th. And this is an image of a snapshot of all the measurements made by all the satellites over 1 hour as we went over the storm here, and then here and here. And you can see the storm is moving from south to north as you progress in time. And then this is a composite over 3 hours of all the measurements that are made, centered on this time. And for these 3-hour measurements, because the storm moves over a course of 3 hours, we re-register all of the samples we look at where the center of the storm is, and we use a relative coordinate system or storm-centric coordinate system, so that each measurement is re-gridded relative to the storm center, so that when you composite 3 hours of data, you don't smear out the storm. These are smeared out over 1 hour, but then these 3-hour ones are less smeared out, and you can really see the structure of the storm better that way, the strong winds near the center, and then the radial decay of the wind speed as you move away. So these are the types of data products that we're using to do the tropical cyclone scientific investigations. And one example of how these data are used for hurricane applications, we're taking these measurements and then we're assimilating them into a numerical weather prediction model that's designed to predict the evolution of tropical cyclones. And this is an example of one of those studies, taking the Cygnus measurements, inserting them into a numerical forecast model, and then looking at what the impact of the forecast is with and without the Cygnus data. And this is these plots are the error in the track of the storm, which is where the center of the storm is, and then the maximum wind speed in the storm, the intensity, and then the minimum sea level pressure, the air pressure in the center of the storm. And the black lines are the control. The control is what the operational forecast predicted when the storm was actually happening. This is done by the United States National Hurricane Center. And this storm in particular, I think it's Michael, this storm in particular, Hurricane Michael, had a very poor forecast for the intensity. You can see this black curve, the error goes way, way up here. This is a 72-hour forecast. There was a huge intensification of the storm that was missed by the Hurricane Center. And when you add the Cygnus data, that's the green line, you can see that the error goes way, way down. And it's because we're the measurements, several times a day in the inner core of the storm do a good job of capturing the wind speeds in the center of the storm, and then the wind speeds will directly affect the latent heat flux coming up from the ocean into the atmosphere, and that's the primary energy source for these large storms. So by tracking the latent heat flux, we're better able to predict the future evolution of the storm, and that's demonstrated here by the improvement in forecast error for the intensity and for the minimum sea level pressure. The track was actually pretty good, the track forecast, so it got a little better, but not much better. Anyway, that's an example of some of the things we're doing with hurricane forecast improvement. And then over land, I mentioned that there's now a lot of studies going on looking at the performance of the value of the data over land. And there's one particular characteristic of the land measurements that's very attractive and has sort of enabled a lot of new investigations, and that's the ability to measure inland water bodies. So I'm going to give you some examples of measurements made of a particular section of the Amazon River, and the first two examples will be measurements made by other satellites that have different spatial resolutions. These are all measurements made in the microwave at a very similar frequency to the GPS frequency. So this first one is measured by the NASA's SMAP passive microwave. This is a radiometer that's on the SMAP mission, and the resolution is about 30 kilometers. And so you can see this main branch of the Amazon and then these tributaries, and it's resolved with about 30 kilometer resolution. The same platform, the same satellite, also has had a microwave radar. The radar no longer works, but earlier in the mission it was working. And this is an image made of the same section of the river by the radar, and it has about 3 kilometers of spatial resolution. And you can see that there's a better resolution of the main branch of the river, and then these little tributaries. You can see some of the smaller ones are better resolved because we have 3 kilometer resolution. So this is 2 examples of the section of the river by other instruments operating in the microwave. And then the third example is the image made by Cygnus of the same section of the river. And you can see that the spatial resolution is much, much better. It's able to resolve a lot of these small tributaries. And one other feature, which is really advantageous for a lot of inland water body and wetland studies, is the fact that this area in the Amazon is heavily vegetated jungle. And these long wavelength, this is a 19 centimeter wavelength, these long microwave wavelengths are able to easily penetrate through the dense vegetation canopy of the jungle and still see the water underneath. Most of these small tributaries are covered by vegetation, but we're able to resolve them just fine with the Cygnus measurements. So that's a very nice capability. Okay, so very briefly, the reason why the spatial resolution is so high over land for the water bodies is because of the difference in the scattering mechanism. So over the ocean, spatial resolution is of order 10 to 20 kilometers. And the reason is that when the surface is very rough, like the ocean surface is, the GPS transmitting signal reflects off of all these different facets. And the surface, if it's quite a bit rougher than a wavelength, then the scattering from all these different facets is essentially the phase of the scattering is essentially random from one point to the next, because the differences in the path length are significantly longer than a wavelength. So if they're all if the phases are all random relative to each other, then there's no coherent addition of the signals, and all you do is add up the power scattered by each one of these little facets to get the total power received by our receiver. And when you work out the dependence on the range, the dependence of the received power on the range goes as 1 over the range from the transmitter to the surface squared times 1 over the range from the surface to the receiver squared. And those 1 over range squared dependencies are just because it's just the power density that's expanding, spherically as you get away from the scattering center. So that's the standard way that the signal behaves over the ocean or over any rough surface. But over a very smooth surface like inland water, which tends to be much, much smoother than the ocean, and in particular smoother than the wavelength of the GPS signals, what happens is the surface acts like a mirror, and you get this this range dependence that's now dependent on the 1 over the square of the sums of the ranges, because there's no breakup of the phase coherence of the scattering in different places. And if you plug in the numbers for the difference in this range versus this range dependence, the difference is about 30 to 33 dB. So it's about 1 to 2,000 times stronger, the signal over water, inland water, than it is over the ocean or over land. And also, if it's coherent, the spatial resolution has a fundamental change from being determined by the time delay in Doppler filters over the ocean to being determined by this reflection property called the Fresnel zone of the reflection, which is of order 500 meters. So the spatial resolution is quite a bit better, and even water bodies that are much less than 500 meters are easy to resolve because the power in the reflections is about 1 to 2,000 times stronger. And that's the reason for the very fine resolution. And here's some other examples of inland water body imaging over South America. This is a Cygnus image, and then this is Southeast Asia, a Cygnus image. And then when you're over land without water, you're also sensitive to the dielectric properties of the soil, which change with the moisture content, and that changes the reflectivity of the signal. And from that dependence, if you look at the variations in the reflectivity over land without water, you can estimate the volumetric soil moisture content, or the water content of the soil. And this is an example of a soil moisture product that's now being generated by the Cygnus mission, and this is a public released data product. These are released every 6 hours, maps of the soil moisture content everywhere in the world, and you can see here that the areas that are wetter and drier, and you can also see the sharp line at about 38 degrees north latitude and south latitude that represents the coverage range for the satellites. Okay, so that's some of the other data products that we've been working on: soil moisture, inland water bodies, and ocean winds, and air sea heat fluxes. And yeah, this is one last example of what you can do with the inland water body images. This is a map of the reflectivity of the eastern part of the United States and the Caribbean Sea just before and after a major hurricane made landfall. This is a reflectivity before. This is a reflectivity after the landfall. And then this is the difference between these first two. And if you zoom in particular on the Dominican Republic in this the island of Hispaniola here, you can see the difference in reflectivity shows up. Large differences are yellow in this plot, and the regions that are yellow are regions where the reflectivity changed a lot from just before to just after the hurricane made landfall. And these are areas that were heavily flooded. There was major flooding and property damage and loss of life from this hurricane landfalling event on the island, and in particular in the capital city, right down in here. It was a major flooding event. So this is another capability that Cygnus has to be able to image flood inundation after hurricane landfalls or after major flood events caused by extreme precipitation as well. So yeah, so these are some of the other applications we're using. And now I wanted to turn back to the ocean microplastics, which is the point of this talk. So, so again, Cygnus measures, what it actually measures is the roughness of the ocean surface, because that affects the scattering cross-section of the surface, and from that we're deriving winds. All right, so what we did for ocean microplastics was kind of turn that relationship around backwards, and we estimated, well, first of all, I should say that, in general, with large storms, major hurricanes and typhoons, that was the point of Cygnus being flown. It's very difficult to measure winds in the middle of these large storms because they change quickly and because there's a lot of rain. And so Cygnus was specifically designed to address those two limitations by having many satellites so we can measure often, and by using a very long wavelength so we can penetrate the rain. Okay, so that's when Cygnus provides unique information about the wind. But Cygnus runs all the time over the ocean, away from storms, and over land. And when you're over the ocean, away from storms, there's many other ways to measure the ocean wind using other satellites that don't have this limitation of the need to penetrate through heavy precipitation, and the ocean winds don't change as quickly. And so what we did was, when we're not over storms, when we're over just the regular ocean, we took the wind measurements made from other satellites, or from, actually we used these reanalysis models that are forced by other satellites, and we calculate what the roughness should be for that given wind speed using these parameterized roughness models. We calculate what the roughness should be for that wind speed, and then we make a measurement of the roughness with Cygnus, and we look at the difference between those, and we call that the roughness anomaly, or the mean square slope anomaly. A mean square slope is a statistical measure of the roughness. All right, so it's how much more or less rough the ocean actually is than it should be given the wind speed at that time. Okay, and it turns out that roughness anomaly we found to be very highly correlated with the concentration of ocean microplastics. And the idea, or the hypothesis, is that the microplastics, or something else that's has the same transport mechanism as the microplastics, is suppressing the roughening of the ocean for a given wind speed. And these anomalies are in general negative. When there's microplastics present, the ocean is less rough than it would have been without the microplastics. So we think that the presence of these foreign properties on the surface of the water are suppressing the roughening of the ocean from the wind. Okay, so what we've done is empirically developed a relationship between the roughness suppression, or the MSS anomaly, and the microplastics, and I'll have a few slides to show you how we've done that. And then once we have that empirical relationship derived, we can then make images, dynamic images of the concentration. And I'll show you a few examples of that. One of them is seasonal variations from month to month and year to year of the concentration in the North Pacific gyre, or the Great Pacific Garbage Patch. And then another is some time-lapse images of the concentration near the outflow of some major rivers around the world. And I think I have some examples of the Yangtze. And also just a couple quick things to mention. One is this: we now have a microplastic data product. It was just released publicly last month, and this is the URL that points to it. It's supported by one of the NASA DACs, the Data Archive and Distribution Centers. So anybody can go to this site here and get these daily images of the microplastics that we're deriving from Cygnus. And then this citation down at the bottom, this is a paper that was done by myself and a student here, Madeline Evans, developing this algorithm. Okay, so again, the idea of the measurements that we make of the roughness, what we actually measure, the engineering measurement by these radars, is the scattering cross-section of the ocean surface. And then the scattering cross-section is related to the roughness through this equation here, which relates scattering cross-section sigma naught, the thing we measure, to the mean square slope, which is it's the second moment of the roughness spectrum. It's a statistic of the roughness, and it's related to this straightforward relationship where the numerator here is the Fresnel power reflection coefficient of the ocean surface, which is straightforward to calculate. And so from that we get mean square slope, and then we estimate mean square slope from the wind, and then we take the difference between that and the measured mean square slope measured with this equation, And then the difference between those is the mean square slope anomaly. And that's the product that we use to estimate the microplastics from. And here's an example of what that looks like. The top plot here is the mean square slope measured by Cygnus averaged over an entire year of data. Okay, and you can see in particular that the mean square slope is strong negative. It's red where it's negative. It's strong negative in the North Pacific Gyre, the North Atlantic Gyre, and then down in the South Pacific, South Atlantic gyres, and also in the Indian Ocean, North Indian Ocean. So these are regions where the ocean is less rough than it would be if there hadn't been anything in the water. That's the hypothesis, and for a given wind speed. And then you can see these regions where there's typically low concentrations, divergence zones, not convergence zones of the ocean circulation. Those tend to have MSS anomalies close to zero, which means the roughness is consistent with the forcing winds. And then the bottom plot, this is an ocean microplastic model predicted by Van Sibyl. There's several different models out there for what the ocean microplastics are, the concentration distributions are, and they're derived from they're derived from ocean circulation models and forced by some injection of microplastics. Some of the models inject the microplastics at the mouths of major rivers. Others have randomly distributed injection of the microplastics, and then the ocean circulation transports the plastics, and they tend to converge in these gyres. I should point out that all of these models are steady state models where they'll let the circulation run for several decades numerically and then see where all the ocean plastics end up. So they converge in some distribution. They don't have dynamic variations, and in particular, they aren't able to resolve seasonal variations in the concentrations. And that's the reason why when we compare the top to the bottom panel, we use an annual average of the Cygnus MSS anomaly, because there's no seasonal variations in the model that we're comparing to. So what we did was we took these regions of high and low concentration, the red box and the white box, and we used those as control regions to develop an empirical relationship between the MSS anomaly and the predicted microplastic concentration predicted from this Van Sibyl circulation model. And that gives us an empirical mapping from one to the other. And the result is this bottom panel. This is our estimate of the microplastic concentration averaged over an entire year by Cygnus. That's the bottom panel. And then as a point of comparison, this top panel is a collection of in situ net trawl measurements of ocean microplastics composited over a huge range of time, several decades. This is all the measurements available of net trawl concentrations up to 2015. And you can see the North Pacific Gyre right here, this high concentration, and then there's another high concentration in the North Atlantic, another one in the South Atlantic. There's very little data other places, the South Pacific, the South Indian Ocean, there's very little data. There's some data here to show that there aren't high concentrations where there isn't a convergence zone of the convergence of the circulation pattern. Also this is all just kind of composited together from all different measurements made all different times of year over many decades. And it's also probably the case, very likely the case, that over this several decades, the concentrations have changed. They've increased over time, so that's not really represented in this either. But anyways, there isn't a lot of ground truth information available about the microplastics, so this is kind of as good as we have. Sorry, and you can see that the higher concentrations here, the lower concentrations near the equator, they're kind of borne out by this empirical retrieval from Cygnus. Okay, so now we took the Cygnus measurements and made an animation over a full year. This is a full year of the concentration derived from Cygnus. I think that's like the daily frame. And so this is the data that's posted on this public website now of the concentration. And you can see things changing over time. And one thing in particular that we saw that we weren't really expecting, but you can see it pretty clearly when you look at it, is that the concentrations in both the northern and southern hemisphere tend to be quite a bit higher in the summer and lower in the local winter, whether it's northern hemisphere or southern hemisphere. And we now have several years of this data that we processed, and it's a consistent trend where the concentrations are higher in the summer, lower in the winter in both hemispheres. And to see if this is corroborated by ground truth measurements, what we did was we took the the net trawl measurements, and that's on the right here. And we divided up all the net trawl measurements over these several decades. We divided, excuse me, we divided them up by month, what month the measurement was actually made. And this is just for the North Pacific, so it's all Northern Hemisphere seasons. And we see that there's much higher concentrations in the summer with the net trawl data and lower concentrations in the winter. So that shows the seasonal signal. And then on the left, these are the average measurements over the North Pacific, South Pacific, and globally of the concentrations derived by Cygnus for each month. And you can see in the North Pacific, the red, there's much higher concentrations in the summer and then lower in the winter. And then in the South Pacific, it's exactly 6 months out of phase. And then the global one is kind of a wash. It's kind of, because you're averaging both hemispheres together. So it's this red North Pacific curve that you would compare to the North Pacific net trawl data. And they have the same general behavior, that higher concentrations in the summer, lower in the winter. So that's, you know, as much sort of ground truth validation or verification as we're able to do with this seasonal dependent signal. But it looks like it's a very consistent signal. And as I mentioned, this is 1 year of data, but we've done this for several years and it repeats itself from year to year, the seasonal signal. Okay, and then the next application is looking at the outflow from rivers. And so we zoomed in on the concentrations that we're estimating near the mouth of the Yangtze River, which is where the city of Shanghai is at the mouth of the Yangtze. So that's kind of right here. And then looking at what happens. So this top left panel A, this is the average, the annual average of the concentration measured by Cygnus over an entire year. And then we went through the year 1 week at a time and to look at whether there's any variations in the behavior from week to week. And although this is the average over the year, we picked the 3 weeks of the year that had the biggest signal, and especially this one right here, you can see this is the concentration in this one particular week in June 2017. And you can see what looks like a large outflow plume coming. This is the mouth of the river flowing out into the East China Sea, and then smaller versions of that outflow plume in other weeks of the year. And so we've done this for all the every major river between 38 North and 38 South. This is the largest signal that we've seen, is the Yangtze, and that's been sort of posited as the probable largest single source of ocean microplastics is outflow from the Yangtze. But we've also seen it in other major rivers. The second largest we saw was the Ganges, and there's similar plots like this for the Ganges in India that are in the paper that I referenced earlier. And then we've looked at other major rivers. We can see a signal coming out. It's not as strong coming out of the Amazon into the South Atlantic. We can see one coming out of the Mississippi outflow in the United States, and none of the others are nearly as strong as the ones from the Yangtze and the Ganges. But we see other signals as well. And yeah, so that's something else that you can do with this data, is look at these outflow events. And then yeah, my last point I wanted to cover is we've also started doing wave tank experiments to try to understand exactly what the physical mechanism is that's causing the suppression of the roughening, that's causing this mean square slope anomaly. And we've done that with, this is a wave tank at the University of Michigan, here in Michigan. And this wave tank has the ability to create controlled roughening or forcing of the surface roughness. There's these large fans at one end that create this laminar flow of controlled wind going across the top to roughen the surface from wind. And then there's also these large paddles that create swell waves. And then there's a lot of these sensors along the surface. These are ultrasonic altimeters, essentially, that rapidly measure the surface height. And then from that, you can get the roughness spectrum. And then we've introduced a lot of contaminants into the water, varying the concentration of the contaminants and varying the type of contaminants. We've done a variety of different microplastics with different number densities and size distributions. And we've also introduced a number of different surfactant concentrations into the surface, and then seen what happens to the dampening. And this is just one example, a control run with clear water. There's no contaminants here. And then we measure the surface height as a function of time, and then take the Fourier transform of that to get the roughness spectrum. And this is what the roughness spectrum looks like. So it's a typical roughness spectrum that you'd expect from a wind roughened surface. And then we introduce contaminants into the surface and then look at this roughness spectrum. And from the roughness spectrum, you can derive the mean square slope. It's basically the second moment of this distribution. So we've done that. And the results are in this paper, which is, it's actually in review now, but it's posted publicly if you're interested in looking at it. And what we found with these measurements is that the microplastics themselves have a very small effect on the dampening of the roughness until the concentrations get very high, much higher than is reasonable to expect in the open ocean. So it's probably not the microplastics themselves that are causing the effect we see with the Cygnus data. But the surfactants, when we add surfactants to the surface, it has a very immediate effect on the dampening of the roughness at very low concentrations and at concentrations that are consistent with what's expected in the open ocean. So we think that what's happening is the surfactants in the ocean are acting as tracers for the microplastics. And the reason why we think that makes sense is the bulk transport mechanisms of both microplastics and surfactants are fairly similar, at least from what we've read in the literature. The bulk transport is caused by major ocean circulation patterns and the major ocean currents, and so they should behave in a similar way. The gyres, where the convergence zones of the current, where the things tend to concentrate, like in the North Pacific, would be common to both the surfactants and the microplastics if they have the same transport mechanisms. And we think that's what we're actually seeing, not the microplastic directly, but associated surfactants. And so that's at least the current best guess at estimate of what's the underlying physical mechanism. And we're continuing to do measurements in the wave tank to try to validate this further. Okay, so this last section of the paper is the presentation is about whether or not we think that this type of technique could also be used with inland waterways, in particular before the river outflow, into the ocean, to be able to track the presence of surfactants or microplastics or anything suppressing the roughness when you're over rivers or lakes. And again, getting back to what I was saying earlier about spatial resolution, over the open ocean, the resolution is about 15 to 25 kilometers, depending on the incidence angle, and it's driven by the bandwidth of the GPS signal and our ability to do Doppler filtering and so on. And this is also the resolution with which we're able to resolve the concentrations in the open ocean, like in the North Pacific gyre. But in inland waterways, the resolution is much, much finer for the reasons I was talking about earlier. And again, this is that section of the Amazon that I showed you earlier that had this really, really high resolution with Cygnus, much, much higher than 15 to 25 kilometers. So we can see and resolve these very small water bodies inland. So that's the first necessary condition to be able to observe the surfactant tracers or the microplastics in inland waterways. Is, do we even have the spatial resolution to do it? And I think the answer is yes from these sort of demonstrated capabilities. And then the next question is, will lakes respond to winds in a predictable way from wind forcing so that they roughen? And then if they do, can we look at roughness anomalies? If we have an independent measurement of the wind, estimate the roughness from that, and then compare that to the actual roughness we measure. And there was a recent paper just last year looking at the response of lake surfaces to wind roughening with the Cygnus satellite measurements. And this is the reference to that paper. And the basic conclusion is yes, we can see it. And this is a particular lake in Central America that we've had lots of flyovers by Cygnus of. And these are measurements of significant wave height, which is a measure of the long wave swell roughness of the water surface retrieved from Cygnus data. And there's a number of validation intercomparison measurements available that are described in the paper to show that this distribution of wave heights is consistent with ground truth measurements and consistent with the direction of the wind. Like, for example, the wave heights are higher at this end of the lake than this end because the wind is blowing from the northwest to the southeast, going in this direction, and that makes the basically the fetch length of the surface is longer towards the downwind side of the lake than the upwind side. So the state of development of the roughness is, is larger because the fetch length is longer and the seas are more developed, and that's the reason why the winds are, or the waves are higher on this end. So basically, Cygnus is able to resolve this. And again, this is a small lake, and yet we're able to resolve some of the features in it. So I think, those are the ingredients that you need: the sensitivity to the response of wind roughening, and the ability to have sufficient spatial resolution to see the the interior of the water body. And so between those two, I think it should be possible in principle to be able to do these types of applications within the water bodies, but it hasn't been done yet, and that's something that we're just starting to work on now. Okay, so in summary, we've made measurements of ocean roughness anomalies with the Cygnus satellite, and we found that they're highly correlated with the ocean microplastic concentrations, at least as determined from these models. And we've seen these seasonal fluctuations in both the northern and southern hemisphere that are consistent with the net trawl data. And we've seen these outflow events happening in major rivers, in particular the Ganges and the Yangtze, and they tend to happen in very small periods of time, and then not after that. It looks like it should be possible to extend this application from the open ocean to these smaller water bodies. We're still working on wave tank experiments to confirm the physical mechanism for the roughness suppression. And that paper, that first paper showing some of the early results is in review. And one set of new things that we're starting to work on now, which looks like it's going to work well, is Cygnus is just one type of radar, and we've started looking at data from other satellite radars over the ocean, of which there's many. They have different operating wavelengths, and all of the others are backscatter radars, not forward specular scatter. But they also measure ocean winds by measuring the roughness. And we've taken those and done a similar sort of process in comparing the roughness anomalies with the other radars to the ocean microplastic concentrations from the models. And we see a similar correlation as we did with Cygnus. And one benefit of doing that is these other radars are in polar orbits, most of them. So we're able to get coverage at much higher latitudes. And with Cygnus, we only stop at about 38 degrees north latitude. So we couldn't really image whether the microplastic concentration drops off again as you go further north above the North Pacific gyre. But with these other satellite radars in polar orbit, we're able to go all the way up to 60, 70 degrees north latitude when we start hitting the ice. And in those images, we can clearly see the roughness anomaly go back to zero, and the derived microplastics go back to being very low when you get above about 45 or 50 degrees north latitude, as was expected. And similarly, in the southern oceans, you can see the drop off at much lower southern latitudes. So that's just more confirmation of the general behavior of the concentration distributions that are predicted by these large-scale global circulation models. And we'll continue to do that work as well. And I think, with that, I'll stop. And thank you very much.
So thank you very much, Chris, for this very nice presentation, this nice piece of work. And I think it's very important, since it opens new perspective in the observation of these microplastics. I think we can start having some questions from the ground. I would ask to the ground if there is any questions. Maybe I can start with one comment. So you mentioned that actually the idea to observe this plastic concentration is related to the anomaly with respect to the normalized radar cross-section predicted by a sketching model forced with ACNWF winds.
Yes.
So I was wondering if you find any, best case in terms of sea state condition or environmental condition, let me say, to make this measurement trustable, reliable. Yeah.
Well, I think if you do the comparison between our measured roughness and the roughness derived from the ECMWF winds, if you do that comparison in the regions of the world where the expectation is that there's very low microplastic concentrations, for example, near the intertropical convergence zone where the currents are flowing away, then the agreement is very good and it doesn't vary much over time. So the anomaly is very close to zero, essentially, and it doesn't have a seasonal signal. So that suggests that the relationship between the predicted roughness and the measured roughness is very consistent and stable. But then when you move away from these regions and you move into the the North Pacific gyre, for example, the difference between the predicted and measured roughness is there's more variance. It goes up and down. It's seasonal. There's all these other things that happen. So in terms of where it's reliable. The relationship is reliable where there's no microplastics, essentially, or surfactants.
Okay. Then I have also another question. So, as far as you understood, by taking care of both the experimental part the in-field measurement with sinus and wait time measurement. So, do you think that there is one scattering mechanism that is responsible to the detection of this microplastic? Let's say the reduction of the roughness, or it can be also other mechanism that involves different part of the sea surface spectrum, because actually, as far as I understood from your talk, actually the reduction of the roughness, so the damping, is actually related to a sort of bioproduct. So basically, the surfactant that comes from this plastic concentration. So it's let me say, is an indirect effect. Is there any other effect that you can imagine related, for instance, to the longer wave part of the spectrum, or no?
Right. So this is it's an excellent question, and this is exactly the thing we're trying to look at now. So with the wave tank experiments, we're able to resolve very precisely the change in the roughness spectrum as a function of the type of pollutant, the type of the concentration of the surfactant, or the number or size density of the microplastics, or whatever. It's a very controlled experiment, and we can see that some parts of the roughness spectrum are affected more than others. Okay, and then with the satellite measurements, the Cygnus has a particular sensitivity to the roughness spectrum that's due to the wavelength of operation and the incidence angle of the measurement, and the fact that it's a forward specular scattering measurement geometry. But some of the other satellites that we're now looking at, they operate at different wavelengths, and they have a backscattering geometry for the measurement. So their sensitivity to the roughness spectrum is different. They're sensitive to different parts of the spectrum, and even Cygnus is sensitive to different parts depending on which incidence angles you use in the data analysis. So what we're trying to do now is take the perturbations in the roughness spectrum as determined from the wave tank experiments, and then relate those to the differences in sensitivity of the different measurement types, the different radars, the different wavelengths, the different incidence angles, to see if those relationships are consistent or not. And that's something that we're just starting to do now.
Okay.
Yeah, but that's an excellent question.
Thank you.
I guess there are some other questions from the ground. I can see some waves. Is there any other question from your guys? I just...
Hello, maybe I can ask a question?
Okay, please.
So thank you very much for the very interesting seminar. You told us that the microplastics themselves have a low effect on dampening the roughness, no? So the surfactants, when inserted in the tank, are the ones that have an immediate effect. And yes, you told us that probably the surfactants are acting as tracers for the plastics, what you are observing with Cygnus, and not the plastic itself. But do you think that these surfactants are present where the plastic is present just because they have the same transport mechanism, or maybe they could be related somehow to the presence of plastics, such as maybe for some microbes colonizing the plastic pollutants or some effect like this. So it's just an effect of the same transfer mechanism. The surfactants are natural and are there with the plastic, or they're produced by the plastic?
Yeah, that's a very good question. I don't know the answer. And I'm not sure how I would try to answer it from the data analysis. I mean, if there were certain, I don't know, regions where one mechanism was more likely and another where the other, where the presence of the microplastics was creating the surfactants because of, so chemical or biological reactions, as opposed to other places where that's not possible and it's more driven by the transport. Maybe then you could try to answer that question with the, empirically with the data analysis, but yeah, I'm not sure.
Maybe the lack of in situ measurement is a problem, maybe also for this.
Yeah, very much so. So, I'm in this, there's a task force it's under the IOCCG, if you're familiar with that organization. It's part of the UNESCO branch of the United Nations. And they created this task force last year to make recommendations about ways that the major space agencies could help the microplastic remote sensing problem. And there's representatives on this task force from ESA, NASA, JAXA from Japan, and ISRO from India. And then there's a number of other people. I'm on it, and some other people that do microplastic related remote sensing. And the report, we're just finishing it up now, and it has a series of recommendations to the space agencies. And one of the main ones is the need for more in situ measurements, more validation, more coordination between the surface measurements and the satellite measurements, and just a whole series of things like that. Because it's really hard to validate these products right now.
Thank you.
Hi, Chris. This is Domenico Schiavulli from UMETSAT. Unfortunately, I was able to connect just 10 minutes before the end due to a 2-year-old lady in quarantine at home, so crazy day. But since I follow you, I mean, because I worked on GNSS reflectometry during my PhD, so I mean, you are like I
know your name. I've read your papers. Yes.
Good, because I thought you knew me just when I went to prison, but no, it's okay. No, I have just a very quick question. This microplastic observation done with Cygnus, do you think can have some benefit working together with the Hydro GNSS mission that ESA is going to start? I mean, can be this the future for GNSS reflectometry to be, let's say, become operational in different application?
I hope so. I mean, the original science objectives for Cygnus had nothing to do with microplastics, and really had nothing to do with land. And similarly with Hydro GNSS, I think the primary science objectives are more hydrology and soil moisture and land processes, right? But I'm assuming that they will never turn off the instrument, I hope. So the data will continually running over the ocean as well. And, if they have the measurement, if they have the system running all the time, 100% duty cycle, and if the data are made available to the, public research communities, then it should be possible.
Yeah.
I mean, I think Cygnus, the most important thing we did, just because it was easier, was to leave the instrument on all the time, even though we only needed the data over the tropical cyclones. The easiest operational mode was to just leave it running all the time, and because of that, we've gotten all these new applications.
Okay.
Yeah, so I hope Hydro GNSS will do that.
Yeah, hopefully, yes, and hopefully this is the first steps for a full operational world for GNSS reflectometry. Thanks a lot.
I have a question, which is, of course, is a comment, more a question, but let me say, let's make simple, okay? The anomaly is due to surfactant. Up to now, we know. This surfactant may be due to the plastic or may be due to some phenomena which collects even the microplastics. So let me say it's kind of oceanography circulation problem which gather surfactants and plastics. So let me say in one sense, the mapping, the anomaly, okay, is a mapping of some surfactants which may contain microplastics. Let's make the, so I don't want to say there is not microplastics, but we cannot say 100%. And it would be nice to test over some area where we have, because it's easier, of course, that we have some, let me say, some surfactants, which may be algal bloom, for example, okay?
Right.
Just to make an example, you know? So
right.
we make the test for the procedure. Of course, the interpretation in terms of microplastic may be challenging. I'm not saying it's easy, but for sure, what you are saying, we have an anomaly which is related to a surfactant. If together with the surfactant there is microplastic, that's another issue. I'm not saying it's not true, but I listened to you, I appreciate your talk, and I love it because it was even physically based, not was only statistic, you know. So, but of course, at the present time, although I understand that there is a large interest of microplastic, we cannot guarantee. It's let me say, probable presence of microplastic, which of course tells us a lot. It doesn't mean that.
So yeah,
that's my point. It's a comment, or if you like a question.
No, I agree completely. And there's actually a very good. There's a paper. I should have discussed it today. I just forgot that there's a paper that came out last summer by Narita Rodriguez at JPL, and she's looking at Cygnus measurements of roughness suppression. A very similar idea, but specifically looking at phytoplankton and algal bloom outbreaks in this one particular event in the Caribbean Sea, you know, east of Central America, or yeah, and she's able to map out the growth of this large algal bloom event that happened in this one particular case, and there's no reason to believe that there's a strong microplastic presence there because it's not typical, and yet and the contours of the roughness suppression match very well with independent measurements of the algal bloom outbreak that were available from some hyperspectral imagers, you know, satellite hyperspectral imagers. So that's a perfect example of a case without microplastics that is affecting the roughness in a very similar way. So it's, you know, if you were trying to only do microplastics, it would be a false alarm, right? Because it's not true. It's something else causing the roughness suppression. So I think in areas where you have a, you know, likelihood of microplastics and a low likelihood of algal bloom outbreaks, which I think the North Pacific gyre is like that. In general, they don't have major algal bloom outbreaks there. Then it's more reliable as a tracer for the microplastics. But in situations where there may be one or there may be the other, it's much more confusing, and the possibility of having false alarms is much larger. So you need extra information. You can't just use the Cygnus scattering information to determine whether or not it's caused by microplastics or associated with microplastics, I should say. So yeah, I think it's a very valid point.
Okay, thank you. I was not contesting you. I was just, there is still a lot of research to be done. It's not all set. It was a comment to Domenico comments. It's probably, we may think about operational service, but today is not ready. Although I understand there is some political pushing about going
right.
to final products. That's, you know, everybody knows this.
Right. Well, like, for example, you know, there's been a lot of work over the years trying to develop, you know, hyperspectral detection algorithms for microplastics with limited success because it's a difficult problem. But there's much more success, I think, with hyperspectral detection of algal blooms because there's a strong, you know, there's a strong spectral signature that you can see from the biology. And so if you couple those two together, you know, the roughness suppression from the microwave radars and the hyperspectral detection of algal blooms, then if the radar sees a large roughness suppression and the hyperspectral imager does not see the signature from algal blooms, then you have more confidence that it's associated with microplastics, maybe?
I fully agree with you. Do you have a polarimetric measurements on sinus?
No, but hydro-GNSS does. So there's a possibility. That will be the first. Hydro-GNSS will be the first multipolarization GNSSR instrument. Yeah, so that's really exciting.
That's a good point for us.
Yep.
Okay. Anyway, I don't want to stop other comments, other question, whatever. Anybody else?
Can I ask the question?
Please, Arun.
Hello. Thank you very much for your wonderful presentation. I just have a curiosity. One of the questions asked by the Nando that the normalized radar cross section, you are relating the microwave plastic relate to the normalized radar cross section of the satellite, which suppress due to the presence of microplastics. Is it okay? Am I get your point?
Well, are suppressed due to the presence
but
of
just a question related to the
right.
Just a question related to the water tank experiment. Did
Yes.
you consider all the scenario, physical conditions, and the physical parameters are considering on that particular experiment? How can you relate? You just want to say that we are justified from the water tank experiment. So are you considering all the physical scenarios or environmental parameters on that experiment or not? Just for the curiosity.
No, well, I mean, it's a very restricted environment. You know, the laboratory experiment, it's much smaller, of course, than the ocean. And so there's lots of scaling arguments you need to make when you relate the roughness spectrum measured in the wave tank to the roughness spectrum that would be measured in the open ocean. There's many scaling arguments that you have to make to relate those two. And we tried our best, but I think the right way to do it, and this is something that we're looking into for next summer, if COVID lets us, is we have access to a much larger wave tank. The one we used was about 30 meters long, and we have access to one that's like 2 kilometers. It's this big one that's run by the United States Navy, and they might let us use it. And then the scaling arguments are completely different, very different, and they're not as important when it gets bigger and bigger because there's less interactions with the edges. And that would be a good test of whether our scaling was done properly, if it works with 2 very different sizes of wave tanks. So that's one thing that we're considering. But, wave tanks, they're very good because they're very controlled and you can do repeatable experiments and everything. But, they're not the open ocean, of course.
Yeah. That's just a curiosity for me.
Yeah.
Thank you. Thank you for your.
Yep.
Thank you very much again. Thank you very much again. I think it was very, very stimulating about the sinus project and satellite, and of course the microplastic monitoring as well. I thank you again, Chris. It was a real pleasure to have you and start in such a good way our 2022 seminar, and I hope we may even have another chance to talk and learn more about this very interesting, let me say, not only in the applicative sense, it's even the scientific sense problem. Thank you again.
Yeah, thank you very much for inviting me.
I can give you all applause to you. Thank you very much. Grazie. Thank you.
Grazie. Thank you very much.
Yeah. All right. Bye-bye.
Thank you. Bye.
Thank you. Bye.
Thank you.